introduce the next speaker, Samih.
Yeah, that's fine.
Kind of like what I was sharing with GM earlier today, it's kind of part of this, and we'll see that later again today with Google. There's this huge shift in how we build graph technologies where we're separating storage from compute, and it's just opening up so much architecturally. And tell me if I'm wrong or whatever, but if you're excited by technologies like Apache Arrow or DuckDB, and how this is just changing how we kind of work with large data on the fly, there's just so much flexibility. To me, this is sort of like the company doing that for graphs. So it's really exciting to have that Samih in here.
All right, so do I speak to the mic or?
Yeah, you get actually, you don't need that.
I don't need to do this?
Oh, you do need
That's for the room. I didn't, okay, I didn't, okay. Well, thank you very much for the intro, and thanks everyone for being here. My name is Samih Sayloğlu. I'm one of the co-founders and CEO of Kuzu Inc., which is the company commercializing the Kuzu graph database. And I'm also an associate professor at University of Waterloo, where I teach databases. So this will be a very much an infra tool, dev tool kind of talk. So I will tell you about Kuzu, which is a state-of-the-art property graph database management system. Primarily because it's based on 7 years of research we did at University of Waterloo in my research group on building fast graph databases before we became a company. And it's a system that's designed to run everywhere. So for example, it's an in-process library instead of a traditional server, and I'll tell you more about this later in the talk. And it's can be a solid foundation for many AI applications, especially if you do RAG, because it has several native retrieval capabilities like a native vector index and a full text search index, and I'll tell you also a little bit about those. So let me start by telling you, giving you an overview of the general data model and the query language of the system. So Kuzu is a structured property graph database. So what we mean by that is that you model your records as a set of nodes and relationships. But unlike the original property graph model of Neo4j, where you can put arbitrary key value properties on nodes and relationships, you have to a priori define the schema of your records in Kuzu. So here I'm showing you an example of how you would define a graph database of, say, financial bank accounts with account IDs and balance properties, and transfers as nodes, so those would be your nodes, and transfers between your accounts, which would be your relationships. So you define these as you define your relational tables as in a relational system, except you identify which one of your tables are node tables and which one of those tables are relationship tables, so you get logically a graph view over your records. And once you model your records as a graph, you can query your nodes, relationships, paths with the Cypher query language. So the system implements Cypher. So a defining feature of Kuzu is that it's a system that aims to give you the Cypher query language from everywhere. It aims to give you access to Cypher from everywhere. So what I mean by this is, for example, we can run, so Kuzu is shipped as a single binary with no external dependencies. We can run all popular CPUs, and it's deployed as an in-process library instead of a traditional server that you spin off. Okay, I'll tell you more about this in the next slide. So it's similar to SQLite or a system like DuckDB. If you're familiar with these systems, I've used these systems. And in fact, a very good way to kind of think of Kuzu broadly is to think of it as DuckDB for graphs or DuckDB for Cypher. And installing it is very simple. It's simply a pip install or an npm install command, and then you can get access to Cypher, start creating your graph databases as in this Python script, and issuing Cypher queries. So I want to elaborate a little bit more on this, because I think developing applications with an in-process database, graph database, can be a major paradigm shift for many developers who are developing database applications. So traditionally, database applications are built with this two-tier architecture. So where there's this sort of monolithic database server process that's running somewhere, maybe in a data warehouse. And you have an app server, maybe a node server that's running somewhere that communicates with this database server through the network. And maybe in modern data stacks, there's also a data lake, maybe that stores data in popular data formats like Parquet files that may also feed your application server. And in front of the application server, you might have a desktop app, a browser app, or a mobile app that communicates with the app server. And this is fine, and you can continue doing this. All right, my slides changed. I am not sure how to get back to my slide. All right, I'll have to wait. Well, I can take questions if there are any.
So what are your plans for GQL and kind of future?
Yeah, so the system currently implements Cypher, and the core of GQL is Cypher. So we don't have the resources to implement a second language right now, but hopefully, over time, we'd like to kind of expand and become also GQL compliant. This was the sort of strategy of Neo4j as well. So my slides are still.
Hopefully people like Victor's talk.
Yeah, so I wish I could tell something about the slide too, but I don't know enough. All right, yeah. Sorry about that. No problem. Right, so again, so this is the classic two-tier software architecture for database applications, and this is fine, and you can continue doing this for some applications. But a system like Kuzu can simplify this architecture for some of your applications in major ways. So for example, you can, for example, embed Kuzu into an AWS Lambda function that can directly, for example, scan your Parquet files into a graph format, and you can do on-demand graph analysis, and I'll talk more about this. And this might, for example, be beneficial if you have these graph database server that's running somewhere and eating cache, and it's not being used too often. Instead, you can do these in-demand, sort of on-demand architectures. Right? You could also put Kuzu directly into your app server. So why might that be beneficial? So traditionally, in this two-tier architecture, you would scale your database servers and your app servers and your load increase or decrease separately, and that might be. But now with a system like Kuzu, because Kuzu is bundled as part of your app server, you only need to care about scaling your app server. There is no database server that you need to kind of manage and administer. Right? And similarly, you can put your Kuzu into your desktop applications, your standalone applications, maybe your Python scripts, into your mobile apps, as well as even directly inside your browser. So Kuzu runs everywhere. So this is what I meant by one of the major design goals of the system being that we want to give developers access to Cypher from everywhere. So one comment that I want to make, kind of clarify a misconception, is that, and I hear this a lot about in-process databases, is that the fact that you're building an application, database application, using an in-process database system does not mean that your databases are stored only in memory and they're ephemeral and they're kind of they're not persisted. Just like any database management system, Kuzu by default persists your data on disk files in its own Kuzu format. But the system supports ACID transactions, so your writes to your databases are atomic and durable, so we give you the core database capabilities. But it also has an in-memory mode if you want to sort of have create databases on the fly that are temporary and ephemeral that are going to be thrown away. So actually, let me kind of tie this with the AWS Lambda architecture that I mentioned in the previous slide to describe an interesting use case that we've seen people develop with Kuzu. So we have seen people who have a very large amount of records in some tabular format. So maybe think of hundreds of millions of records. And for various reasons, they cannot create a single graph database out of these records. Okay, so for example, in one case, there was a compliance reason that the customer was unable to commingle data across multiple users. So what they were kind of destined to do is that they had to create tens of thousands of small databases. And each one would be used quite infrequently, and each one would be quite small. So, and you can't really maintain sort of thousands of sort of graph database servers that are running somewhere waiting to be queried. So the user instead went for an architecture that looked like this. So they put these small databases in Parquet files, because they had ETL pipelines already, into an S3 bucket, where, for example, in this case, I'm showing you, think of this as like some users and the phone calls that they made, and they're stored in Parquet files. And on demand, when the analysis was needed to be made, they span off a Lambda function that embedded Kuzu, scanned these Parquet files to create an on-the-fly temporary graph. They did their analysis and wrote the results back to S3, and they forgot about this database. So sometimes you've also seen people, instead of using an S3 and Parquet files, instead use an operational large database like a Postgres server that's running somewhere that maybe has got billions of records. But at any point in time, the graph database that they need to query and create is kind of a tiny fraction of this, so Kuzu can directly scan from Postgres, so they would create these on-demand graphs. So I call this like creating an on-demand graph cache of your records when the need appears, and it could, for example, the point I'm trying to get across that it could simplify your architectures. You could get creative by building these software architectures in your databases. Another misconception that I want to clarify is that the fact that the database system that you're using is in process also does not mean that you should use it for small data. And in fact, first of all, you should never trust any database company that says that they have a fast and scalable database, because everyone says this. I understand this, so I want to be guarded against that. I do encourage people to actually use Kuzu on very large databases, and primarily because for 7 years prior to us becoming a company, that was exactly the question that we studied in my research group. How do we develop a fast graph database that can manage large amounts of records? And that's essentially the situation where a system like Kuzu shines. So Kuzu integrates a lot of state-of-the-art sort of principles of how graphs should be managed and queries, and we've written many articles on these. So I do encourage people to actually try Kuzu on very, very large graphs. So here's kind of one performance point that I want to show. This is showing the performance of our data ingestion, which is bulk data ingestion, which is done with a copy from command, which is similar to Postgres' copy from. And it's on an AMD 7551 processor, which is not even a very fancy processor. You can buy this with less than $100 nowadays. And this is the speed of ingesting the largest graph analytics benchmarks in LDBC, which contains 447 million nodes and 17 billion edges, and creates a 0.5 terabyte database, and we can do this in less than an hour, in 58 minutes. So I do encourage people to try Kuzu on large graphs. I think we would pleasantly surprise you with the speed that we can provide. Now let me switch gears and tell you a little bit about the retrieval capabilities of the system. So Kuzu has a natively built HNSW vector index, which is disk-based. So natively means that it's not like a dependency to Lucene or something. It's completely 100% built within the system, using actually Kuzu's storage structures itself, and I'll tell you a little bit about this. And I want to kind of go through the retrieval capabilities through an example. So suppose you have a set of documents, and in many RAG applications you would chunk these into smaller pieces. So you have these chunks, and maybe each of these chunks, which are text, you are being embedded into some vectors. And you might also, through a separate process, extract some entities out of these, so maybe some persons. So these arrows means that those two chunks are referring to a person named Ellis, those other two chunks are referring to a person named Bomb, so on and so forth. So you may have created these entities as well. You could model this data as a graph database in Kuzu as follows. You would have chunk nodes, which have the string contents as well as the embeddings of those contents using the text encoder you used. You would have person nodes, which are the Alice, Bob, etc., the entities that you extracted, and you could have mentions, relationships between those chunks to persons. For each chunk, an edge, a mentions edge to the person that they have extracted. So this could be the DDL statements and the schema of your database, and maybe this is your actual database of records. So those red nodes are the chunk nodes with string text and embeddings, and the blue nodes are the person nodes. So in Kuzu, you could create a vector index out of the chunk nodes, which have these embeddings, the vector embeddings, using a call function called create vector index function, and you give your vector index a name, and we'll take these chunk nodes and create an HNSW index. So if you're familiar with HNSW indices themselves are graphs, so we actually use the core storage structures of the system to implement the index as well. Now you can do several types of retrievals in Kuzu. You could do vanilla vector search. So you could, for example, find the k nearest neighbors, say 100 nearest neighbors to a particular query vector. So give me the chunks that are closest in terms of this vector embedding in the vector embedding space to a particular vector. So for example, if you're building a chatbot and someone asks, what does Alice enjoy doing on the weekends? You could encode that query as a vector and then call this function in Kuzu, call query vector index, and give the embedding of your query vector, and you could get the 100 nearest neighbors just as in vanilla RAG. You could also do filtered vector search. What this means is that you're looking for a k nearest neighbors, not across all vectors and chunks you index, but across only across a small subset of them. So if this is your HNSW, you might be interested in nearest neighbors only across a subset of these nodes, or maybe those highlighted nodes over here. So you do this in Kuzu with this project graph call, which identifies a subset of the nodes through some filters. So in this case, this line over here is saying where you're identifying only the chunks that have the string Alice in their content. Okay? And then you can pass that chunk Alice projected graph into the call query vector index function to only find the nearest neighbors within that subset of chunks that have the string Alice. So you're kind of doing this filtered search within your subset of vectors. Okay? And because Kuzu is a graph database, you can do hybrid graph vector search. So you can, for example, find 100 chunks whose embeddings are closest to a particular query, and then do maybe graph traversals around those chunks to retrieve other chunks. So for example, you could say, give me the 100 nearest neighbors of a particular query vector, plus all chunks that mention the same persons as those chunks. So for example, if this chunk was among the 100 neighbors that were returned, you could do a 2-hop traversal to also get this green chunk. And you would do that by essentially following your query vector index function call with regular Cypher pattern matching to retrieve other chunks. Right? And finally, I want to say that Kuzu is a very data science friendly, especially Python friendly database. We can scan data from many different formats, including Python in-memory data frame objects, data lake formats. We can directly scan your delta lakes and delta lake tables and iceberg tables, as well as some relational tables. And we can output to many formats of data science tools, like we can output your query results into pandas, polars, or arrow, as well as say like NetworkX or PyTorch Geometric, some of these popular Python graph analytics libraries. And in fact, one of the common cases that we see Kuzu being used is it's a component of a larger data pipeline that uses multiple of these data science libraries in Python. So this is an example that's using Kuzu, Pandas, and NetworkX in the same script, because all of these are libraries. You could put all of them into the same Python script. And as a first step, you might be doing some data transformations in Pandas, getting a data frame, and you can pass that directly to Kuzu. So these two lines are Kuzu queries, where that df parameter is a data frame. That's a Python in-memory object. But because Kuzu runs as part of the same Python process, we can directly scan your data frame. So you don't have to essentially output your data frame to another format, which has obviously performance advantages, but it's also very convenient to kind of build your entire data pipeline this way. And we can output your results with a single function call into a NetworkX object. So this G is a NetworkX object, which you can then sort of, now you're in NetworkX, you can run NetworkX function, maybe you're running a PageRank function, and turn that into a data frame and give that back to Kuzu. That's again Kuzu, to store those PageRank values back in Kuzu. So the point I'm trying to get across is that notice the seamless passing of Python objects in the same Python process in and out of Kuzu, and this is what I meant by Kuzu being a very Python-friendly graph database. We got several other features. You can, these are our language bindings. I'm not going to go through all of them. You can run Kuzu inside your browser directly because we have a WASM version. We have a native full-text search index that implements the BM25 ranking algorithm. We have a graph data science, a suite of graph data science algorithms like PageRank, connected components that will be released in 2 weeks. We have several third-party visualization integrations, and all of these features are available under the MIT license in the open source. As a company, we do support and consultancy contracts, and we are designing our enterprise and cloud version. So if you're interested in building graph database applications and would like to be a design partner, we'd be very happy to talk. So here is our sort of links. Start us on GitHub, and I'm happy to take questions. Thank you very much.
So
well, happy to kick it off. So, cool. Yeah, happy. So, thank you for presenting. For a lot of us doing investigations and OSINT work, we will, a lot of these like RAG and vector systems are kind of assume things are in memory and charge you by RAM essentially, which works when you have like a million things and you're doing like some e-commerce recommendation and you have a million products and that's fine. But in investigations, we might have billions of things. And so all of a sudden, charging by RAM gets a little expensive and prohibitive for a lot of people very quickly. So I'm curious if you have any comments on supporting large-scale vector search.
Yeah, so we can index vectors that are bigger than RAM because our index is a disk-based storage. As I said, like Kuzu's vector index uses Kuzu's disk-based storage structures. We have the disk-based, if you're familiar, CSR-based sort of storage structure to store graphs, and HNSW is a graph. So we use that, which means that your graphs, your index can be much larger than your available memory. So Kuzu will scale out of memory for indexing large vectors. Yeah.
Do you support any geo pandas or like any geospatial data extensions? So not data frames per se, but GeoPandas data frame.
Excellent question. So currently no, but we have an extensions framework. So Kuzu is like Postgres, where there's a core Kuzu and there's a bunch of like the vector index, full text search user extensions. And one of these extensions we plan to have geospatial data support and geospatial indexing support actually. So it's in our medium-term roadmap, but yeah, it has not been implemented yet. All right.
Okay. Well, thank you.
Thank you very much.
Speaker.